I may get things wrong, and I guess this is just like the preface. Also, I recommend that you have the paper open next to the presentation if you can, just because I might refer to some things in the paper and might not have screenshots for everything. So that's it. So this is the article, The Design Principles of the Elixir Type System by Giuseppe Castagna, Guillaume Duboc, and Jose Valim, the creator of Elixir. And this is sort of like before they got started with integrating types or static typing, I guess, into Elixir in version 1.17. They sort of released this paper where they went over like the theory of you know, how they plan to integrate types into Elixir. And so basically, what's the motivation behind it? Well, initially, I guess, this is sort of how we could define Elixir. You see that Elixir is in the top right in the dynamic strong typing section with Erlang and Ruby, I guess like the two major inspirations in terms of programming languages for Elixir. And basically there are 4 categories. There's 2 ways you can divide programming language type systems, right? So they're either strong or weak. So in weak systems, a variable can sort of fluctuate between different types. In JavaScript, for example, you have like type coercion. And then in C and C++, you can take the pointers and modify them so that you're essentially just like changing on the fly what a type is, or what the type of a variable is. Whereas in strongly typed programming languages, once you assign a type to a variable, it stays that type. You can't change it on the fly, really. Or I guess, yeah, you have like conversion functions, but those are semantically different. And then the other way to divide typing systems is either static or dynamic. So a static typing system will well, during compilation, there'll be a type checking step where the compiler will go over all the types of that were specified in the code and make sure that there aren't any inconsistencies related to that. So, for example, you can't call you know, an addition function on something that isn't an integer, for example, if the addition is defined only on integers. Whereas dynamically typed languages will only check those things during runtime. So, you know, your code may compile and run, but it's only once the addition during execution receives something that isn't a number that the error will be presented, I guess. And so the motivation of this paper is essentially how can we take Elixir from a dynamically strongly typed language into a statically strongly typed language. So we're just sort of, you know, moving into the other box. Or I guess because it's gradually typed, it would be sort of on the border between statically and dynamically typed. So why would we want this? Why would we want to add static typing to Elixir? Well, static typing gives us added safeguards and guarantees about our code. We can check that certain things are true given given a code. For example, that certain invariants remain constant throughout like the whole execution of the program. We can prove that these things are true based on the guarantees of the type checker, and this allows us to essentially prevent bugs, right? And also, you know, it's cool to be able to infer, you know, additional information about our programs from the type specifications. So the type specifications are essentially contracts that we give, that we sort of have side by side with our code that say like, oh yeah, our code is going to do this. We guarantee that, you know, this function is going to return this kind of type, and we guarantee that, you know, all these variables are consistent with these types. And so what are set theoretic types, right? So in the paper, the authors present the typing system that they'll adapt for Elixir, and the typing system is set theoretic types. And what are they? So just as a refresher, I'm going to go over algebraic data types, which is a very, very common kind of composite data types, which exists all over different functional languages, and that you probably have heard about before. And it'll give us, I guess, the foundation for jumping into set theoretic types afterwards. So in algebraic data types, essentially you have three basic type constructors, right? So you have it's the three last rows of my table here. You have the sum types, which are essentially enums or options. It's how you might have encountered them in your programming languages that you've used. You've got product types, which are like tuples or structs, records, pairs, and then you have arrow types, which are functions. And in algebraic data types, you can create new types essentially from the types that you already have using these constructors, right? So you can say, for example, that I'm creating a new type that is either an integer or a string using a sum type. Or I can say, well, I'm creating a new type that is a collection of three integers, for example, and that's going to be a tuple, a product type. Lastly, you can create functions. You can create new types by saying, okay, well, I'm going to create a function that will take an integer and return a string, for example. And all of these are new types that you build out of your basic data types, which are your singleton types, so true, false, or atoms. In the case of Elixir, you have your empty type, which is the type which contains no values, so you can never instantiate anything that has the empty type. You have booleans, which can have two values, true or false, or bytes, which can have 256 different values, for example, a character. And we say that they're algebraic data types because you can do algebra essentially on these data types. There's a sort of correspondence between a type and the number of possible values that can be instantiated for that type. For instance, the empty type corresponds to 0, the singleton type corresponds to 1, booleans to 2, etc. And the sum type of two singletons, for example, will have a number associated with the sum of the numbers of the singletons that you're combining, right? Here. So, for example, if I create a boolean, if I create a function, that takes a boolean and returns a boolean, I'm essentially exponentiating, or actually I'll do a tuple of two booleans. There's four possible values because it's 2 times 2 values, right? You have, two choices for the first boolean, two choices for the second, and then your tuple therefore has 4 possible values. As an example of why it's called, algebraic. Furthermore, because it's algebraic, you also have distributivity. So these are examples of the algebraic data types in different languages. On the top left, you have Julia. On the bottom left, you have C++. So here we can see that, we have enums for our sum types and structs for our product types. And then on the right side is all Haskell. And it's all different ways of expressing essentially the same data types. So again, you have enums at the top. But then your data ice cream, which is your sum type of a sum of product types, can be expressed either as a product of int and flavor, or in the last box on the complete bottom right, it can be expressed as a sum of 3 different products, right? So here you can see that it's sort of distributive, right? So that's the algebraic part of algebraic data types. Now, back to set theoretic types. It's similar to algebraic data types in the sense that it is a composite data type, so that you're using these constructs to make complex types out of the basic ones that are given to you. However, instead of mapping to algebraic terms like plus, multiplication, and exponentiation, you're using set theory. So you have unions, intersections, product sets, so like Cartesian products, subsets, and complements. So in this set theoretic type system, you can sort of see a type as a set which contains all the values that can be instantiated in that type, right? So this is sort of like a reminder of the different set theory operators that exist, right? On the top left, you have intersection. Middle of the top, you have the union. And then on the top right, you have the complement, which all have corresponding operators in the paper that's presented, right? So you have your and, your or, and your not. There we go. Actually, I'll just check. Are there any questions so far? Does anybody? I don't have the chat, but perhaps somebody could tell me if there's. Okay. So everything is clear so far. I feel like I'm sort of steamrolling through this. Okay. I think I'll just keep going. All right. So that's our set theoretic operators, and we have the corresponding operators in our in the way that we can define types in this in what's presented in this paper. And this gives us very interesting consequences. For example, subtyping corresponds to subsets, right? So for example, in the examples that they give in the paper, they give the example of the false type, which contains only one element. It's a singleton. It only contains the false value. You also have the true type, which contains the true value. And both of these types together, if you do the union of them, then you get the Boolean type. So the Boolean type contains two values, and it's the union of two sets that each have one value. Furthermore, you can also take the union of integer and Boolean to get integer or Boolean. Sorry, it's because I said and, so I got mixed up. But by taking a value that's either an integer or a Boolean, you're essentially taking the union of these two sets, and you make one larger set that is a new type that has all the values of both integer and Boolean. He gives this example in the paper here, and I tried to illustrate the example, although functions have like a weird sort of type in this new set theoretic typing system. It can sort of be seen as like the set of all mappings from all the ways to map the values from one set into another, into like your initial set, your domain into your codomain, right? So, but that gives like sort of weird semantics when we get to and, right? When you have to take the intersection of functions, you end up with like this weird situation where you have like the set of all of the functions that map integers to integers can also map Booleans to Booleans or Booleans to other stuff. And so that's why this second type works, is because the set of all the integers that map to integers also can map different values to other things. And so when we take the intersection of these two things, well, then we have all the functions that map the integers to only integers and the Booleans to only Booleans, and it's not an empty set, right? So that is sort of weird to wrap your head around, I find. Again, you also have the distributivity, as I mentioned earlier, with algebraic types. Well, we still have this in set theoretic types. And here's the example that's given in the paper. So you have these two different types, T and S, which are defined in different ways. So you either do the product of this union type and the Boolean, or you can do the union type of two products, and you end up with the same type. So by defining this function that takes a function from T to T and S and returns S, because this is sound, we know that both S and T are essentially the same type. And so that's I guess that goes into my next point, which is the reason we want to use these like complex sort of type systems, right, set theoretic types or algebraic data types, is because we want to be able to verify that two types are the same without looking at just the syntax. For example, these two types have completely different syntaxes, yet the system can sort of, like the type system can understand that they're in fact representing the same set. And so that's an advantage we have with set theoretic types. For example, Raku, which uses like composite data types that are based on like their syntactic representation, can't do these things that we can do with this proposed type system. Now, to go over the basic data types that we're working with in this proposed typing system, again, you have the singleton types that were presented, true and false. You have the universe type, which is essentially the set which contains every other value. So all the types are subtypes of term. And then you have the empty set, which is none, which contains no values. And then you have your integer, your Boolean, stuff like that. And then the paper also presents types that have variables in them, right? So that's when we get into parametric polymorphism. We can parametrize our types, so essentially have variables inside of our types. And these are absolutely essential if you want to do any like higher order functions, like generic functions like map and reduce, which we would like to apply to any kinds of arrays, right? Not just, we wouldn't want to have like a map that only works on integer arrays, right? And then another map that works on string arrays, and having all these different maps defined. We'd like to just define map once and it works for every kind of array. And so by having parametric polymorphism, we can do this, right? And so this is the first kind of type constructor that I'm presenting. Obviously, it's not really the first, because functions like arrows are technically also type constructors, and like and like all the set theoretic type operations are like type constructors. But I guess this is the first like that I'm presenting explicitly. Anyways. There's also, and I feel like this is one of the lacks of the papers, is they didn't really mention recursive data types. So that would be kind of important if we wanted to do like define lists in general. And I'm sure that it's possible, because they're using lists in the definitions of the types here. But yeah, that might be something that comes in the further developments, as I'm going to mention later on. Then you have protocols. So protocols are equivalent to like the Haskell type classes or traits in Rust, or protocols in Swift, or interfaces in Java, etc. It's like it's a way of defining constraints on your types. So for a type to implement a protocol, it has to have like certain functionalities that have to be defined for that type. So for example, the protocols that they give in the paper are JSON encoder, CSV encoder, and XML encoder, which means that for this new type, so for something to be an export type, it has to have functions defined for it that will allow you to encode JSON from it, encode CSVs from it, or encode XML from it, and encode XML from it, sorry, because you have the AND operators here. And so this is like a new notation that gives a lot more expressivity when it comes to the protocols, because not only can we define a certain protocol, but we can also create new protocols out of the ones that we already have, which is pretty special. All right. And so up to this point, everything that I've sort of explained is everything that I said related to set theoretic types have already been introduced by other researchers, namely for the CDUCE programming language. But then there's, the authors for this paper had to take what already existed and extend it so that it works with Elixir. Namely, they added support in the type system for array of functions, guards, records, gradual typing, and they also explain what else needs to be added to completely support Elixir. But with the gradual typing, they can sort of stop their work here and, add the rest later on. So for functionality, it's just like a new notation that was added that allows you to specify like, okay, we're only, this type requires that the function supports a certain number of arguments, right? By using the parentheses. They also mention, like, this is a quote from the article. This requires a non-trivial modification in the set theoretic interpretation of function spaces. And I think that this sort of goes back to the confusion I had related to subtyping. So because, you know, the set integer to integer could also include functions that map other things to other things, this resulted in a like weird interpretation of this second type. And I think that, you know, it's directly related to this problem here. And Appendix A sort of goes into more detail, but I didn't have the time to fully understand the appendix. So moving on from that, there's the guards and the pattern matching, which were added to the type system. So they added the ability to infer types from guards, which is actually like really hard. As they explain, like the guards can be like really substantial and sort of complex, and so you have to like generate an environment and go through each of the guards and sort of populate that environment with you know what kind of type you'll be giving, but you also want to give a type that's like as specific as possible, right? You don't want to say like, oh, it's just going to be a term, right? And then, you know, your type system is useless. And so they also have like exhaustivity checking and redundant case checking for pattern matching. So making sure that you're covering all the cases and that you don't have cases that are redundant. You also have narrowing. So when they are inferring the types from the guards and the pattern matching and the patterns that you specify, like that they're the most specific types possible. And sometimes also it's sort of like ambiguous what kind of type it is. So they can use conservative approximations. So essentially they use like the widest set possible or the narrowest set, and they continue the inference with both of them. And that sort of allows them to make sure that, you know, their exhaustivity checking and the redundant case checking still works, even with like this sort of ambiguity that can exist for some types. This is the example in the paper for the exhaustivity checking. So as you can see, you know, they do some pattern matching here on the value R, but they don't handle all of the values here. For example, if R is of this shape here, well then, you know, the function doesn't handle it. And so this is possible to check. This is possible to discover at compile time now because of this type system. All right. So there's records and dictionaries. After that, there'll be gradual typing, and then we'll sort of reach the end of what's been added, what's been contributed in this paper. So records and dictionaries. So here, you know, we're covering maps in Elixir, and there's like two kinds of maps. So either a map behaves as a record when a key has to exist, or it acts like a dictionary when, you know, you can sort of call a value, and if it doesn't exist, it'll just return nil. So when it acts as a dictionary, it's sort of like in Lua, whereas when it acts as a map, it's really like a, I guess, a struct, or I guess a record in other languages. So a record expects a key to always be defined, and so that's going to affect how the type system handles records. But then you also have fetch, which is a function that's defined on maps, which sort of behaves in a complementary way to records. So records expect the key to always be defined, whereas fetch only has to have the key be defined sometime, right? And then obviously dictionaries don't necessarily need a key to be defined at all. And so in dictionaries also, you can have like anything is a key, or there are certain types that you can use to index into dictionaries, which make the typing system a bit more complicated. And in the paper, they sort of go over how to handle these cases, or at least some of these cases. And then lastly, they show like how you can handle deletion of elements inside maps using the type system. And so for that, they use actually the complement set theoretic type, which is type operating, which is cool. All right, lastly, gradual typing. So gradual typing just means that we're adding this whole effort, this whole paper seeks to add static typing into Elixir, right? But instead of doing it all in one go, and especially because there are still more work to be done, gradual typing is essentially a way of saying, okay, well, some parts of the code are statically typed, and other parts will be dynamically typed. And in their proposition, they're saying like, okay, you can sort of specify which parts of the code will remain dynamically typed, and so which parts will be ignored by the type checker, right? And so this is essential if you want your new typing system to work with previous Elixir code, as Jose Valim has been like very adamant on. It's also essential in the transition from untyped Elixir into statically typed Elixir or optionally statically typed Elixir. You need to have this gradual typing that will allow you to add more and more functionality to the typing system as it's developed. And so this new dynamic type sort of encapsulates all of the parts of the code which won't be type checked at compile time and will continue to be type checked dynamically during runtime. And this is also going to be this also has to be handled by the type checker, which will have to sort of propagate the dynamic type because it's sort of like infectious, right? So if you don't have any guarantees for a certain part of the code and they interact with other parts of the code, well, then those new parts will also not have the guarantees. However, you can still use guards to ensure that some parts will, even during runtime, be of a certain type. And so this sort of ensures your strong typing guarantee. So this is back to the first slide that I had on strong versus weak typing. Because we have guards, we remain in the strong typing category, and we don't have weakly typed Elixir, right? All right. Sorry, I sort of skipped to the end there. All right, so that's it for what the authors added using this paper. Now they also gave like a formalism. So this is like a formal way using Backus-Naur form of defining the syntax of Elixir. Obviously, Elixir syntax, it does not look like what they presented here, but it's like everything can sort of be reduced down to what they presented, and then using this like reduced form or like no syntactic sugar form of Elixir, they explain some of the parts of the typing system using Genson's notation. But this is like, I don't want to give a lecture on, like I haven't planned on giving a lecture on these kinds of formalisms, so I'm just going to like go over this section. If anybody wants to talk about this, feel free during the discussion to bring it up. But yeah, I'm just going to skip over this, I guess. All right, now for the integration into Elixir. This paper came out before any typing got implemented in Elixir. And since then, there have been two versions that have added some type checking to the compiler, namely 1.17 and 1.18. In the 1.18 release notes, which I have over here, they sort of go over all of the difference that have happened in the type system here, in the type inference that they've added in 1.17, and then what's new in 1.18 with regards to the typing. But even with all of this, it still isn't possible to annotate functions or really anything unless you're using typespec, as you could do before 1.17. You have to sort of rely on what the compiler can infer for now, but this is still fine. It's able to find bugs in your code that couldn't be found before because of this new typing system. And in future versions, there'll certainly be the possibility of manually specifying the types for your functions and your values, and then that can go into the type checker, which will then be able to make sure that those promised types are actually respected in the code. Lastly, second to last, there's the related work, and this I'll also sort of go over because in the paper I feel like it's pretty clear. It's just essentially a list of what other programming languages do and what other research exists that's somewhat related to adding types into Elixir. For example, the different efforts there have been for adding types into Erlang, and other languages that have sort of like similar type systems to the one that's been being worked on in this paper. But yeah, if you have any questions about this as well, feel free to talk about it during the discussion. And then lastly, the further work, what the authors say, it still needs to be developed to have like a full statically typed Elixir. Namely, there's it needs more complete type inference. Right now, the type inference is honestly, in my opinion, it's still very nice. And it covers a lot of cases, but there's certainly things that need to still be worked on. It also needs to add row polymorphism and key types. So row polymorphism is, for instance, if you want to do a function that does like element-wise addition, right, for arrays of any size, well, then you need row polymorphism to sort of for it to work on arrays of any size, right? Otherwise, you need to sort of like, have a type for a function that works on different sized maps. And also key types. Also, I guess like one of the core aspects of Elixir and Erlang is message passing and concurrency. And that hasn't even been touched by any of the typing that was presented in this article, which, I think is unfortunate, but also, understandable. It's not evident. There has been work with regards to this using behavioral types, which is like a weird, like linear type system, I think. And more specifically, they mentioned mailbox types, but I haven't really looked into mailbox types. And then lastly, behaviors, which is another core part of Elixir and Erlang. So far, the typing system that they presented hasn't really interacted at all with behaviors. And they have like a pretty lengthy section, I think like a full page in the article dedicated to talking about, how to add typing to behaviors, or I guess what are different like strategies that can be used for this. Yeah, here the whole last page. All right, so that's the end of my presentation of the article. Here's some information about me. I like to keep this for the end because I guess you can decide whether or not, based on the presentation, whether you want to retain any of this information about me. And so that's all I have for the presentation. Are there any questions?